Bonjour, I am Jannathul Raihana, Syed Mohamed, a first-year student from the School of Physics majoring in pure physics. For this video, I am the scriptwriter.
Konnichiwa, I am Nur Shazlin binti Zamri, first-year student from School of Physics, majoring in pure physics. I am editor for this video.
Tajahau, I'm Zafirah binti Amin, a first-year student from School of Physics, majoring in pure physics, and in this video, I will be your presenter. Let me bring you to explore this one interesting device called Superconducting Quantum Computer. Superconductors and quantum computers are two topics you may have heard about independently. Superconductors are conductors that at extremely low temperatures can exhibit zero resistance. They have a massive effect on superconducting transformers, particle accelerators, and high-speed trains. Quantum theory is used in quantum computers to process information. It has reached the apex of data processing. But surely there must be some disadvantages to such a fantastical existence. We will discuss one of the primary issues with quantum computers in this video, the price of cooling them off. You may have observed a cooling mechanism such as a fan or something similar even in typical CPUs. Modern smartphones alert the user if the device becomes excessively hot. This prevents overuse from melting silicon chips in the circuits of these gadgets. In order to cool down the overheating electronics that could result in the loss of millions of dollars, the typical supercomputers used by Intel and Google require enormous room-scale refrigerators. Water is used in liquid cooling to cool the servers. Combining liquid cooling and air cooling is frequently done using a computer room air handler (CRAH). But in addition to the many billions of dollars spent on their purchase, this also requires expensive installation and upkeep. Superconductors being used in quantum computers is an idealization of the current state of affairs. The mechanism behind these computers stem from using superconducting phenomenon in the qubits of the quantum computers. Unlike the conventional computers, which uses bits, the binary system to function, quantum computers can also include the superposition of the two binary values, hence generating more accurate data. Superconducting quantum computing devices are typically designed in the radio frequency spectrum, cooled in dilution refrigerators below 15 millikelvins, and addressed with conventional electronic instruments. Superconducting qubits have fast gate times, which means similar computations can be performed much more quickly than on other qubits, for example, ion trap. This is important since useful computations will likely have millions of logical gates. Additionally, the technology behind superconducting qubits can take advantage of existing methods and processes such as printable circuits that we have already spent years improving. As a result, it is much easier to envisage a scalable superconducting quantum computer than with other existing methods. Superconducting qubits have fast decoherence times, meaning their memory is very short-lived and we need more correcting qubits to compensate. Since superconducting qubits can normally only interact with the handful of qubits next to them on the device, we need extra operations to perform most algorithms. Finally, each superconducting qubit is slightly different and must be calibrated, which could cause problems on larger systems. The last century has seen more scientific development than ever before. With the enormous amount of data we receive every single second, we need better computers to analyze and organize this data accurately. Google produced the Sycamore quantum computer, which performed a task in 200 seconds that would have taken 10,000 years on a classical computer. Quantum computers itself has been a huge breakthrough in the last decade. As an improvement of quantum computers, superconducting quantum computing may become a norm in the near future.